I've called this video Earth's Curvature Plainly Visible. Or is it plainly? Oh boy, that's me trying to be clever. I've always wondered if I had that grammatically correct, and it turns out I did. Back when I posted this on my blog, it was back in 2020, and there it is. It's called The Earth's Curvature Plainly Visible, 10 examples. And what I'm going to do in this video is talk about and show what it took to produce the information that you see on this photograph for that first example, viewing Philadelphia from Apple Pie Hill in New Jersey. Okay? And why? Why am I making a video now? If you followed my channel, you'll see that I've been making survey-related videos, not flat Earth debunking videos, because that's what I don't do that. As a surveyor, I wanted to show information that I don't think people are seeing in some of these other videos, like a video like this one, claiming that there's missing curvature. And there are a bunch of these videos. There's a lot of them out there. So on my channel, you'll see videos going back to 2016, 17, 18 in that, and different types of projects that I've done in different places like Lake Pontchartrain, Utah, the Bonneville Salt Flats, and up in Maine at Cadillac Mountain. I've done a lot of surveying work to show that we can easily measure the Earth's curvature. Why make a video now? Because I thought I've covered it all. I'm making this video now because I'm still seeing lots of flat Earth acceptance based on these kinds of videos, these missing curvature type of videos. And the people who are accepting it, it shocks me and surprises me when I see online people that I otherwise would think would know better. They're highly educated. They have an enormous amount of discernment in a lot of areas, questioning things. And so I get surprised and shocked when I find out that they've accepted that the Earth is flat by watching videos like these missing curvature kinds of videos. So here's what I want to do in this video. I'm going to focus on this whole idea of seeing too far, missing curvature. I'm going to talk about the 8 inches times the distance in miles squared formula. We're going to go into where does it come from and how is it to be applied. We're going to talk about measurement uncertainty and surveying instruments. Apparently, there's this idea out there that the surveying instruments are inaccurate in some way and that they are to be dismissed and that they cannot produce accurate results, which is surprising because as you'll see shortly here, you can't have it both ways. And then I've got a fun surprise at the end. And please feel free to leave comments on topics for future videos. This is a screenshot taken from this particular video. And again, there are a lot of them. You could look up a bunch of these kinds of videos where they show the elevations of mountains. And that's what I was thinking about when I wanted to insert the topic of measurement uncertainty and surveying instruments. Where do these elevations come from? All right, where did they get these mountain elevations? Well, it came from surveying. So it's interesting. They're going to quote the elevations of mountains and accept them, but they're also going to discount or dismiss surveying instruments and the ability to measure. But the measurements were made to determine the elevations of the mountains. So again, you got to reconsider here. You got to really look at this. You can't have it both ways. Here's a triangulation diagram showing the connection made across the English Channel to connect Great Britain with France for the purpose of finding the relationship between the meridian through the observatory at Greenwich and the observatory at Paris. And that's a really cool map. And think about the effort made to do that. And also at this stage, I'll mention that all of this information is digital, online, available. So it's not only the maps, but it's the books, the reports, the actual field notes taken at the time where they measured all these sight lines. This is all available. You can look at it. And I'm bringing this to your attention because I don't think those other flat Earth videos are talking about that. So I'm offering this information for you to look into and consider. And as a matter of fact, the links are in the description box for you to look at as you will. And there's a lot of information available there. So let's recognize that an enormous effort was made to do this type of work, all of this triangulation. Check out that instrument on the left. It's gigantic. We don't use instruments like that today, but this is what they used back in the day. And look at the amount of effort it took over there on the right. They built these huts to house the instrument and house the people up in these mountains. And to make these observations took time, took a long time. And in modern triangulation, and by modern I mean, after the 1700s and 1800s into the early 1900s, you could see that the instruments are smaller now. So the instruments are being refined, and no longer do you need a big three-foot diameter type of an instrument. And they had the ability to raise the instrument using these bilby steel towers that they would erect for the instrument. And also, these towers were being erected, at the remote locations that were being measured too. On the left, you could see a person up on top aiming a light. So these lights would be aimed at another tower that a theodolite was occupying to measure these angles between all these towers. And these sight lines are 10 miles, 20 miles, 30 miles, 50 miles, and in some cases up to close to 100 miles. Here's some examples of triangulation in the United States. I like this map. It's the triangulation on Long Island Sound. You can see the sight lines across there. And then, like I said, the maps don't come first. What comes first are reports where the measurements are made. They're recorded in field books. They end up in a report. The calculations are made, and it's all available for you to take a look at. Here's a map showing all the triangulation across the United States. All these, those are not red lines. Those are arcs of triangulation of little teeny tiny lines. All right. I like this website. This is Zhanna's Survey Station, and I've got the link in the description box. And she has done an enormous thing. She took great effort to make available to everyone all these older historic triangulation diagrams, control diagrams, and other maps. Really nice. So you can go there, look up your state, like New York in this example, and get PDF of these particular maps and take a look at all the measurements that were made in your area where you live. There's also triangulation diagrams for all the states. And I see she's got Greenland on there. And, we're going to need that one. Chuckle. Oh, boy. Principal triangulation of Great Britain. I'm showing you one map. There are a bunch of these maps. You can look them up. It shows all the sight lines that were measured. And look at the instrument used back then. A gigantic theodolite lugged around, set up to measure all these long lines. This is an enormous effort. Again, huge reports, all available, digital, online. Take a look. Here are the pillars in Great Britain, and they erected these pillars all across Great Britain to put the instrument on and measure those sight lines. Here is the Great Trigonometrical Survey of India. And look at all of the triangulation effort that took a lot of time, a lot of years spent lugging that giant theodolite around to measure all these sight lines. Now, So now we talk about these heights of mountains. Okay, well, here's the northern arc of that triangulation through India. And you can see all the sight lines going up to the peaks of all these tall mountains in the Himalayas. Mount Everest is there. This is how the measurements were made, and then the calculations made to compute the height of Mount Everest. And it becomes, the question is, if you're going to show the elevations of the mountains in these flat Earth videos claiming there's missing curvature, do you accept those elevations or not? And also, if you do accept the elevations, well then, how can you reject the surveying that was done to determine those elevations? So you can't have it both ways. Think about that. And at each of these intersections, where you see all these lines coming together, they were occupied by an instrument sitting over top of some type of reference mark. And here in the US, most of these are brass discs like this one. And the information is available for each disc. The date it was set, the measurements made, you can get the reports for these, and you can look at all this information. There it is. It's something that you may not have known, and it's worth thinking about, considering. Let's look at the effect of triangulation over time on the making of maps. I'm using New Jersey as an example, but you could look up lots of different countries. And here's the example on the left. Older maps, 1300s, 1400s, 1500s, they are a little bit cartoonish. They kind of look like the land in question, but you can tell they're not, quite right. So they did the best they could, however they did that. It wasn't until triangulation came along, and look at the middle map. New Jersey isn't completely triangulated yet, but there's the amount of observations made at that particular time for that map. You can see that the state is taking better shape. And then over time, more triangulation occurred. You could see on the right, the state of New Jersey starts to look like, well, what we recognize as New Jersey. And each of these triangulation diagrams that you can get for yourself at Zhanna's website that I showed you. There are insets for further detail. Let's zoom in on one of these. You can see all the sight lines observed for that triangulation, and also to the lighthouses and other aids to navigation that are out in the bay, because they had to know where they are and they had to know what height they were. That's it. I mean, it's just that simple. Now, the next stage, or the next thing that happens after the triangulation is completed and you have a rigorous network of survey control stations, you then start to produce topographic maps based upon topo surveying. Topographic surveying is an enormous effort where crews have to come in and start to locate all of the roads, rivers, streams, lakes, ponds, hills, everything. So you can see here on the topo map, and by the way, this would be a topo map that you could get for hiking. You probably have bought these in the past if you're going to take a hike in your area. So, all the towns are shown and all the county boundary lines and township lines and things like that. Well, look at this map. If you look closely, there are little triangles there. Those are the triangulation stations. And also, you can see little BM symbols. BM is benchmark, and that's where the leveling took place to establish the elevations through that area. And then from that, you see, I missed one. Look, there's one right there. Benchmark, 3971. All right, anyway, you can see all the contours are here. That's how we get the relief to show on the map. And that's, I guess, a little summary or background on surveying, this type of surveying, to produce the maps. And that's where the elevations came from. So now you know. So now let's look at the formula, the 8 inches times the miles squared formula? Where does it come from? Well, it's found in old surveying books. Here's one of them, and you can find lots and lots of old surveying texts as PDF files that you can download and take a look at. It's quite interesting. I have a huge collection of these. You'll find it tabulated. Here's a book of tables and formula, and you can see in the contents here is just one page of all the tables that are in this book. Why tables? Well, because this is pre-calculator days, so you had to have some way of hand calculating things, and it was useful to just have tables of information that you could apply in your calculations. And over on the right, you could see trigonometrical altitudes, or it's the drop of the curve from the different distances in feet on the left and in miles. As the distance increases away from the observer, the drop distance, of course, increases. There it is, tabulated. Here's an old book where it actually, I highlighted it in yellow. They're actually talking about the 8 inches times the distance in miles squared. Also mentioned is refraction. And refraction, sometimes you'll hear flat earthers say, refraction is the cause for the apparent curvature you're seeing. It's actually quite the opposite. Refraction flattens out the curve. It lessens it slightly. And so, and I'm going to show you an example of that coming up. Well, nowadays, and by the way, so I've been just showing you older instruments, non-electronic types of instruments where the calculations had to be made by hand. Today, the instruments are electronic, and they have the ability to just put that formula right on into the instrument to help, correct the measurements being made. And that's what I'm showing you here. You can look up all kinds of surveying instruments online and find out their specifications and how to operate them and what accuracy they are and things like that. So here's an example of refraction. I've heard 2 things. One, refraction causes the curvature. Well, actually, no, it lessens it. So reconsider that. And I've also been told that surveying measurements are inaccurate. It's better to just go to a body of water and put a stick there, like a 2-foot stick, and put another stick across the body of water. And if you can see the stick, that means the Earth is not curved. The Earth is flat. And that isn't enough for me to convince me that the Earth is flat, because we have the ability to measure the Earth's curvature quite easily. So here's my refraction example. This is at the Bonneville Salt Flats, and this is the Great Salt Lake, which is like glass. And I made some measurements there. And this one really shocked me. It surprised me. The instrument is set up near the water. It's about 5 feet above the water. And when I looked through the telescope, I saw the mountain floating above my crosshair, which was pretty unexpected. And I was really, I thought there is something wrong with this instrument. So I took the instrument away from the water and went up onto the causeway, which is higher. It's about 20 feet above the water. And I ran that instrument through its collimation tests to make sure there wasn't something wrong with it. And I found out, no, it's fine. The instrument's fine. But anyway, I made measurements from that vantage point as well. And now you could see that I'm about 20 feet above the water. And of course, things look better. So this tells you right now that surveyors do not put their instruments down in the refraction zone near water expecting to make good measurements. You can't do it. It's not the place to be. As a matter of fact, look at the Bilby steel towers. They erected 100-foot towers to get up above, so they could see further. Anyway, it's quite interesting that down near the water, the mountain is floating above the telescope crosshair. Up on the road surface, or up at the roadway, the crosshair is above the mountain, as would be expected. So Anyway, if you want to look further into that, it's example number 4 in that blog post. So that's my refraction example. I've done the 2-foot stick at the water and found that that's not the way to make observations, and it's not the way to make conclusions about the shape of the Earth. And so please think about that. Take a look for yourselves. All right, now let's get into measurement uncertainty. If you just literally search on measurement uncertainty, you're going to find lots and lots of resources, PDFs, classes, courses, all having to do with the topic of measurement uncertainty and as it's applied in all sciences, anything having to do with measurement of any kind, there's uncertainty in the measurement. And our job is to quantify it, determine the precision, and, that's what this topic is about. And if you want to research surveying measurement error analysis, it's the same principles applied directly to surveying, and lots of information out there on the internet. And the books that I relied on through my career are these and others. I have other books, and they all go into the analysis of survey measurements, for the purpose of quantifying the uncertainty in the measurement. And so surveying measurements, what are they? Well, with a theodolite, you're measuring vertical angles, also known as zenith angles. If you measure from the zenith down to the horizon, that's called a zenith angle. If you're measuring from the horizon or the horizontal, that's called a vertical angle. So it depends on how you have the instrument set, or in my case, it's a wild T2 theodolite that's measuring zenith angles. But they are measured in the vertical plane, be it zenith angle or vertical angle. It's in the vertical plane. Horizontal angles are measured in the horizontal plane from one object to another. And it could be, in this case, these surveying instrument, survey tripods are set up with some targets on them. Or in the case of triangulation, it could be a distant target or a mountain peak, whatever. If you can see it, you can measure. If you can see two objects in the distance, doesn't matter how far away they are, you can measure the angle between them. That's what theodolites do. If you're talking about an instrument that has a built-in distance meter, distance measuring type of an instrument, like an electronic total station, then in addition to the zenith angles and horizontal angles, it's also measuring slope distances. Okay? So to these measurements, you would apply the uncertainty. You would have to know plus or minus. Did I measure this angle? No measurement is perfect. You have to quantify the amount of plus or minusness in that measurement. Okay? So I bring this up because the folks who have bought into and believe that the Earth is flat and want to discount surveying measurements because they're inaccurate and other claims like that, well, that's just not right. You can't just say it's not capable of making a determination. No, the correct thing to do is, what is the plus or minus value in the measurement? It's not entirely unacceptable. You just have to know, how good is the measurement? Is it plus or minus an inch? Is it plus or minus 10 feet? You just can't discount it entirely and go, oh, it's inaccurate. But that's what happens. That is what's happening. The other thing about it, and I'll pause here for a little bit more on the surveying measurements, the instrument that you choose has to be precise enough to do the work that you're being asked to do. If you're being asked to do millimeter type of alignment in an optical tool setting, you're not going to use an instrument that is just adequate for doing topographic mapping. No, you have to pick the right instrument. Of course, the cost goes up and the effort goes up in making those measurements to achieve the requirement for that project. So that's where that's how that works. You begin with the project specification. What, do you need things to the nearest foot? Do you need them to the nearest tenth of a foot? Or are we looking at, hundredths of feet. What are you asking for? What's the repeatability? What's the positional tolerance you need? That's going to indicate what type of instrument you will use and how many measurements it takes to achieve those results. That's surveying. That's what we do as surveyors. And with leveling, it's a simpler instrument. It isn't measuring angles of any kind. It's really just set up to establish the horizontal line of sight. And you're basically taking differences in elevation between rods and that type of thing. So that's what a level does. An instrument known as a level could be an auto level or just a spirit level, which are the older types that have a vial, a bubble there, and that's called a spirit level. So the instrument that I used to take the picture for Apple Pie Hill to Philadelphia is a Topcon. Let's look at it closer, an ATG2. So that's the instrument. And what I wanted to do was show you that you can look up the specifications for different instruments, for theodolites, for total station instruments, and levels in this case. And so I looked it up and I wanted to know, well, what is the accuracy? And they didn't give it to me. So I wanted to know what is the accuracy in 100 feet or 30 meters, if I'm talking millimeters. I don't know why, but these first three instruments, they don't show it. So I'm going to go ahead and use that value for a less accurate instrument, which would be a conservative approach. I'm going to use that value to do the computation that I'm going to show you in a little bit with that photograph from the blog post, looking at Philadelphia from Apple Pie Hill. I could have also used this value here. That's a little more complicated. Accuracy in 1 kilometer double run leveling. I could have done that, but I'm taking the conservative view that, hey, I'm going to use plus or minus 2 millimeters in 30 meters. So why Philadelphia? Why did I choose Philadelphia as one of these examples? It's because of this flat earth video that I saw back in 2015. And it's called Flat Earth Proof 3 Land Ho. And in that video, they're showing you all these different places around the world where, there's missing curvature here and missing curvature there. And then it comes upon, at this minute mark, Philadelphia, Pennsylvania from Apple Pie Hill. And I'm like, Apple Pie Hill, we used to go up there as kids all the time, climbing the tower and all this. There's a fire tower there. And I looked at this photo and I said, this isn't even taken from Apple Pie Hill. It's probably from an airplane, really. So here's funny. You got this flat earth proof video where they didn't even go to Apple Pie Hill to verify their claim. So it's interesting. Anyway, it prompted me and it got me interested. And so I went up there on November 20th, 2015 with my T2, it's a 1 arc second theodolite. I went up there and I measured zenith angles to the tallest visible structure that I saw in Philadelphia. And later that turned out to be the Comcast building. I didn't know it at the time. And then I set my telescope to 90 degrees, that is horizontal, and made a sketch showing where my crosshair intersected the building. And on the left, you can see the sets of zenith angles that I measured from there. And that was it. And then I went home. I didn't think at the time to take a picture through the telescope. So it didn't occur to me that I could hold my phone up to the eyepiece, which is not easy to do, by the way. By the way, there's my instrument sit up there on the tower. And this is a Wild Heerbrug 1 arc second theodolite. It doesn't measure distances and it doesn't have any software in it. It's strictly an angle measuring instrument, vertical angles and horizontal angles. So then I went down to the Camden waterfront along the Delaware River because I wanted to know what is the elevation of the building I was looking at. And so I didn't want to take that from any other source. I went and measured it myself. There's the Comcast building, and there's me observing the building corner, the tops of the building corners, and recording all that. And with all of that information, with the zenith angles measured from Apple Pie Hill to the building, and also let me zoom in a little bit. Here's the baseline that I made at the Camden waterfront to triangulate. I was able to calculate, and this is surveying software. I'm not looking things up in tables, and I'm not hand calculating. So I brought all my information into my surveying software to compute the elevation of the Comcast building. And when you do that, you have to input your surveying standard error estimates. Remember, we went through it all, measurement uncertainty and so forth. No measurement is perfect. You have to estimate the tolerance of the measurements, of your setups and everything. And you input all that. You could also think of it as, like I said, surveying measurement uncertainty. You input that information when you do the calculations so that you end up with your plus or minus, I guess that's the quality indicator, you could say, that the elevation is 100 feet plus or minus 1 foot or something like that. That plus or minus is the uncertainty part. And, again, think about that. Again, your application, if you needed something done and you just want to know the reliability to the nearest foot, you wouldn't hire someone to come in and measure everything to the nearest millimeter. That would cost an enormous amount of money for no reason. It wouldn't jive with your purpose. And likewise, the reverse is true. If you had some factory and you have to align some machinery in that factory to very tight tolerances, you probably wouldn't. You would have to hire a metrologist to do it with very precise equipment. You wouldn't just hire, a land surveyor he's never done that type of work, and he just does, I shouldn't say just, he does boundary surveys, topographic surveys, but he's not working in and familiar with the millimeter world. So again, that's the whole thing about measurement uncertainty. I think I've said enough on that. Anyway, I at some point realized, I should get a photograph through the telescope. So I went back in April of 2016, and this time, I just wanted to get a picture. I wasn't going to make any measurements, so I just brought the auto level with me, the ATG2, and went up there, and there it is. And I took a photograph through the telescope just to show where the horizontal is striking through that building, and there's the Comcast building right there. All right, so now I have all the information to produce this photograph. So I've got my photo, and I've got my distances, my elevations, and I can now show the drop of the curve, which by the way, I never did. When I put the blog post up with the 10 examples, I never did this part. I never, here's the drum roll, the moment we've all been waiting for. I never went ahead and showed the drop of the curve. I wanted to see if anybody else would bother to take the information and do this part. I don't know if anyone has. If you have, leave a comment in the comment section that you did do it, and see if you come up with what I'm about to show you, okay? And then, of course, there's the other 10 examples. There are the other remaining examples. So the drop of the curve is going to be measured there, right? That's where it calculates from. And here's what I came up with. It's 703 feet using the formula for 8 inches times the mile squared. 8 inches is 0.67 feet. And that's without refraction, okay? And then if you want to account for refraction, I come up with 600 feet. Let's round off. It's 598 is the value out of the calculator. And that's using the curvature refraction formula with refraction considered. You can see it diminishes it by 1/10 of a foot in a mile. right? So that's the 0.57 value. There it is. Curvature, drop, without refraction. The uncertainty using the 2 millimeters per 30 meter calculation at 171,000 feet is plus or minus 11 feet. And the crosshair elevation uncertainty is surprisingly only 0.16 feet. So there it is. Have a look. So now you know what to ask. Where's it measured from? When you see these flat Earth videos and they're talking about the missing curvature and all this, you could start asking, well, where's the line? You know, where are you measuring that from? You are now equipped to ask that question. And the only thing missing are these lines, or the line. I'm guessing here. Where are you talking about? Where is it? But none of these flat Earth videos claiming missing curvature and using the 8 inches times the mile squared formula show you the line through the photo where the drop is to be measured from. Now you can ask that question. Now you know. And then you can also ask, are you applying that formula correctly? You know, most of these videos use the 8 inches times the mile squared formula, and they're talking about, they account for it as being the hidden amount beyond the horizon. And that's not what that formula calculates. So that's just wrong. And now you know. All right? And it's calculating the drop right there. So now you know. So now you can go back and look at these videos and ask that question. And you can think about that yourselves. I hope you do. And then, of course, you can go do some work yourself. If you can't buy a theodolite, maybe it's too expensive, but you can get a hand level. This one's $12. And it's just used for rough grading. But it at least lets you look out into the distance. You can look at something 20 miles away, 50 miles away, and you put this up to your eye and you keep both eyes open, and it's got a level vial in there, and it's going to show you a crosshair going across the scene that you were looking at, and you're going to be able to say, that's my eye level extended into the distance, and it's plus or minus, I don't know, 100 feet, but you're looking at something 50 miles away. So it's a useful item to consider, grabbing one of these, $12. If you and go out and do some hiking, take a topo map with you, have some fun, and rethink your position on accepting the flat Earth because of these flat Earth types of videos. And there's also apps for your phone that you can put in there and get yourself the horizontal established, and as you look out into the distance. And then check my work. Okay, I've got these examples. There's other ones up there. Looking at New York City from Fire Island Lighthouse, that was fun. Here I am at the Delaware Bay, looking at the lighthouse across the bay from Broadkill Beach. Oh, by the way, these are just the top photo. Each of these blog entries shows all of the work done, all the measurements made. I went and surveyed the height of the lighthouse. I didn't accept it from any other source. I surveyed the lighthouse elevation. Anyway, so there's detail at each of these. This one I already showed you, the Salt Lake. Here's the example of 1 mile. People were concerned I wasn't either measuring far enough or I was measuring too far, and someone suggested a mile, so I did a mile. And that's all there in that number 5. And by the way, the targets and the instrument were set up at the same elevation. Okay. Think about that. Like I said, I put these things up there just to present the information to see if people would take a look and evaluate it. You should do that. Number 6, using the lake as the elevation reference, the level reference, I mean. And number 7, looking at that building across, it's really across the Atlantic Ocean because New Jersey kind of curves in, and you're able to, from Wildwood, look right across the ocean to Atlantic City. Number 8 is down at Lake Pontchartrain, looking at that building, the Marriott building across the lake. And Soundly's camera elevation is there. Anybody following Flat Earth know who Soundly is. Example number 9 on my blog is made by someone else. So I didn't want to draw attention to him. Maybe he doesn't want to have that notoriety right now. So it's his work and it's clearly identified, but I'm just showing you mine. Check my work. I loved his example, number 9. It's great, but you should take a look at it. And then this one here was the last one I did, was looking at New York City across Long Island Sound from 48 miles. That was amazing. Now, here's some fun. Let's end with a little bit of fun here. The Gleason map. I took a TIFF image of the Gleason map and I rectified it in my mapping software to rectify it to the azimuthal equidistant projection. That's what I did. You can see that here. And then, by the way, this mapping software has every kind of mapping projection you could think of is in here. Transverse Mercator, Lambert's, all of the different kinds of mapping projections are in this software. So when you're measuring distances on the Gleason map, you can see that yellow line. When you click on one point and you start going across the map, the line is curved because it's obeying the mathematics of that projection. Okay? So let me draw attention to that. That's that red line. But you'll see constantly people measuring. Oh, and there's the length. There's the length. Just zooming in. Let me back up. Down on the lower left, the length of the line shows up. There it is. Okay, so there I am measuring from someplace in Australia to someplace in South America. And but you'll see constantly people measuring on this map with these straight lines. Doesn't work. That's not compatible with the projection that you're using for this particular map, right? So I don't know if anybody's ever mentioned that or brought that up, but I thought I'd present it here. And then let's have some fun. Just saying, yeah, that's wrong. That's right. And here's the Gleason map flipped over. I recentered it so that it's at 90 degrees south now. And you'll notice that the ice wall has formed the continent of Antarctica. So this is the Gleason map flipped over so that south is in the center. And here it is centered on Philadelphia near where I live. And that's what it looks like when you do that. So just a little fun to end the video with. And remember, everybody, all maps are flat. The Earth is not. Have a great one. See ya.